a graph is called a forest if it has no cycles, okay? Or the other word, so a word for a graph with no cycles is to say that the graph is acyclic. So acyclic, G is acyclic if it has no cycles. And we call a connected forest a tree, okay? So basically a forest is just a bunch of trees, naturally. There are no animals or anything like that, just trees. Okay, so this is like what a forest looks like, basically. You know, it's some sort of, I mean, these things look like trees, kind of, right? Okay, you know, you've got these kind of branches, and so this is basically, you know, this is what a tree looks like, and a forest is like a bunch of, you know, components which are all trees. And if you look at, so trees will have some vertices of degree 1, and a vertex of degree 1 is called a leaf, naturally, right? If you go down the branch of a tree and you get to the very end, what you have a leaf. So hopefully these definitions are natural. So, yeah, when I did my master's degree, my supervisor used to always, or occasionally would say, you know, he has this saying he likes to say, which is a great thing about trees is that they have leaves. It turns out to be very true. So let me prove that trees have leaves. So what I want to prove is that every tree with at least 2 vertices has at least 2 leaves. Okay, so remember, a tree is a connected acyclic graph, connected graph with no cycles. So, well, the way we're going to prove this is kind of by doing something very similar to what we did in Dirac's theorem, even though this is a very different context, a very different thing we're proving. So we take a tree with at least 2 vertices and let x1 up to xk be the longest path in T, right? That's exactly what we did in Dirac's theorem. Take the longest path and let's analyze what happens. So I claim that if I look at x1 and xk, first of all, they're not the same vertex. Well, maybe that's clear because it's a path. So this is true. Well, okay, it's not necessarily true because it's a path. So the longest path could be a single vertex, right? But so why is the longest path not a single vertex? Any thoughts? So I've got a tree with at least 2 vertices. Remember, tree equals connected graph with no cycles. I take the longest path in the tree. Why does that path have to have at least 2 vertices on it? Maybe this is a kind of a weird thing to ask, but it is kind of important here. Well, okay, maybe I'll just say, I mean, here we're using the fact that there's at least 2 vertices, right? Take 2 different vertices, and we're using the fact that the graph is connected. So if I take 2 different vertices, there is a path that goes from one to the other, and that would be a path of length, a path with at least 2 vertices. So the longest path has at least 2 vertices. Okay, so that's not terribly interesting, but I'll give the reason here. So these are not the same vertex because the number of vertices is at least 2, and T is connected. That's basically what I used. Now I claim that x1 and xt are both leaves. So that I claim that they both have degree 1. So can anyone see the reason for that? So I take the longest path, I look at that vertex. What would happen if the degree was 2? Any thoughts? Yeah, so there's a proposal in the chat that we could make a longer path. Something like that, yeah. I mean, well, why would it make a longer path? I mean, remember in Dirac's, you know, theorem, we didn't say, when we were proving Dirac's theorem, we didn't say that the vertices at the end were leaves. Like, we didn't prove that they had, yeah, there you go. So that's, I think, the whole argument then. So if, let's say x1 had another neighbor, which was not x2, like some other neighbor, either that neighbor is not on the path, but that's a contradiction because you get a longer path, so that can't happen. Or x1's neighbor is on the path somewhere, and it's not x2, it's somebody else, but that makes a cycle, so that can't happen either. So therefore x1 and xk are both leaves, because, you know, the case of xk is just symmetric, right? You can do the same argument for xk. And so these are 2 different vertices, they're both leaves, so therefore every tree has at least 2 leaves, as long as it has more than 1 vertex. Okay, Any questions about that? So that's just a very simple property of trees. Okay, so it turns out so the way I've defined trees is probably the most standard way to say that a tree is a graph that's connected and it has no cycles. But there's a lot of different equivalent definitions of a tree. So we're going to look at a few different definitions. So we're going to prove that these things are equivalent to being a tree. So first of all, we're going to prove that a graph T is a tree if and only if it holds that for any two vertices u and v, there's a unique path in T that goes from u to v. So this is a characterization of a tree. So in other words, if I have a graph where every pair of vertices has a unique path, then that graph must be a tree, and vice versa. Also, another equivalent definition is that a graph T is a tree if it's connected, but if I delete an edge, so here I mean for every edge E in the edge set of T, if the graph T minus E is disconnected for every edge E of T. So what do I mean by T minus E? I'm not sure if I ever defined this sort of thing, but here I just mean the graph you get from T by deleting the edge E, okay? And another equivalent definition, which is kind of related to the third assignment, is that a graph T is a tree if and only if it's connected and it has exactly n minus 1 edges where n is the number of vertices. So where n is the number of vertices in T. We might not prove all different directions of these equivalences, but you should be aware that all of these things are equivalent to being a tree. So let's prove one of them at least. Let's prove something. So what I want to prove now is the following claim, that if T is a tree, which of course is the same as saying that T is connected and acyclic, right? That was our definition. Here I've just got the definition of a tree, and I want to show that if T is connected and acyclic, then that implies that there's a unique path between any two vertices. Okay, so this was the first condition, or the first equivalent definition on the previous slide. Okay, is it clear what we're going to try to prove? So, okay, assume that T is a tree. Take two vertices, u and v, let's say. I want to show that there's a unique path between them. So what I have to show is that there is a path between them, but there's only one, right? I want to prove that there's at least one path and at most one path between those two vertices. How do I know that there's at least one path? Okay, I've kind of got it written on the slide, but so between any two vertices, there's at least one path because T is connected, right? By definition of a tree, it's connected. Therefore, for any two vertices, there's a way to get from one vertex to the other. And if you take the shortest walk between them, then that's always going to be a path. So now we need to show that between any two vertices, there can't be two different paths. Okay, we're going to do that by contradiction. So here we're going to go, we're going to show by contradiction that if I had two different vertices, you couldn't have two different paths that go between them. Okay, so we assume that there are two such vertices, u and v, and that there's two different paths that go from u to v. So I'm going to call those paths x1 up to xt and y1 up to ym, where the first vertex of this path is, of both of these paths is u, and the last vertex is v. So the first vertex here is u, and the last vertex is v. Here the first vertex is u, the last vertex is v, and I'm assuming that these are different paths. So there's some place where these paths deviate from each other. Is it clear what I'm trying to say? So can anyone see where this is going to go? What's going to be the contradiction here? So I'm assuming there's two vertices in the graph with two different paths between them, and I want to get a contradiction. And really my only assumption is that the graph is a tree. So where's the contradiction going to come from? Yeah. So basically, so I think there's a lot of different answers which are sort of equivalent here. Maybe one that sounds different. It might be equivalent, I'm not sure. But exactly. The idea is basically we're going to take these two paths and kind of together, those two paths are going to give me a cycle, which will contradict the fact that there are no cycles in a tree. The details are a little bit annoying, but let's look at a picture anyway. Because the thing is, all I know is that these two paths are different. They're not I don't know that they're different at every point, right? So you kind of want to think about the picture you think of first, maybe, is that these two paths are like, you know, starting at U down here, let's say, and going up to V, and they're completely different. But that's not really the picture, because, you know, the paths can intersect in lots of different ways. So, you know, maybe the picture looks like this, right? So maybe both of these paths, so I've got a red path and a blue path, they start at x1, or sorry, at U, they end at V, and maybe the blue path, let's say, is the x1 up to x whatever t, and the red path is y1 up to ym, and they can do a lot of kind of deviating, right? They can start the same, they can split apart, come back together, split apart, come back together over and over and over on their way to V, right? And these would be two different paths. But yeah, here's the thing. So basically, you can see in this picture, though, there are cycles, right? This is a cycle, for example. So to do things formally, we have to find this cycle. But it's kind of clear, I hope, from the picture that it exists, right? So formally, what we can do is look at the first vertex, or sorry, the first point where the two paths deviate. And that must exist because these are not the same path, right? By assumption, we're assuming these are two different paths, so there must be a point where they deviate. So this will be, so R is like the first index where these paths differ. This will be my XR. This will be YR. Sorry, and this should be R here. Now we want to find the place where they come together. And if you think about it, okay, but first of all, like is it clear that R exists? Like R must exist, otherwise they would have to be the same path. That kind of connects to one of the comments in the chat about them having to be the same path, right? If there's no place where they differ, then they have to be the same path. They're not the same path, so this R must exist. There must be some minimum place where they differ. So differ meaning like that xi is not equal to yi. Yeah, now we want to look at where they come together after that point. So this should also be an R, sorry. So this should say yr plus 1. But basically, I want to look after the point, after the rth step, and I want to look at the first point where there's some xj, so let's say that's xj, which is on the path, on the y path. So let's say that xj is equal to y, p for some p. So basically here we're letting s be the smallest index, j, such that j is bigger than r. So that just means that we're looking after the point where they split, and xj is on the other path. And so this will exist because, for example, the last vertex of both paths is v, so that's one point where the two paths are the same. So there's always going to be some place where they become the same, and I let that be xj. And then we just look at this, let that be xs, sorry. Anyway, the notation here is just a little bit annoying to nail down because these paths can come together and leave each other over and over. But hopefully the idea is clear, right? So the thing that you guys said in the chat, which was that it gives us a cycle, that's completely true. You just have to be careful how you find the cycle. Okay, are there any questions about that? So if you are a tree, then between any two vertices, there's a unique path. So that's a fact that we just proved. Okay, let's prove. So now we proved like the definition of tree implies unique paths between two vertices. Now let's prove that unique paths between two vertices, any two vertices, implies that the graph is connected, and if I delete any edge, it becomes disconnected, okay? So our assumption now is that there's a unique path between any two vertices. That's our assumption. And our conclusion is that the graph is connected, and if you delete any edge, then it's disconnected. So is it clear what we're trying to prove? Okay, so assume that there's a unique path between any two vertices of T. T is a graph. Well, first of all, so I've got some stuff written here, but before that, why is T connected? So why is this true? Assuming the statement in yellow. Maybe what I'm asking you is too trivial. People don't want to even dignify it with a response. But yeah, so there's a unique path between any two vertices. That in particular tells us that there is a path between any two vertices. if you have a graph where there's a path between any two vertices, that's the same thing as being connected. So t is connected because, because there's a path between any two vertices, because I said that there's even a unique one. So now let's prove the more interesting thing. So suppose I let E be an edge, where E is equal to, E is UV for some U and V in the graph, some vertices U and V. So I want to prove this by contradiction. I claim that T minus E is disconnected. Why? So if it was connected, like what would be wrong if it was connected? So suppose that, so I have this edge UV, which I delete. So what would happen? So what would be the problem if the graph is connected still? Yeah. Yeah, exactly. So if the graph is still connected after deleting the edge, by being connected, there must be a path from U to V that goes somewhere. But then if I go back to the original graph T, that path is still there, okay? And this would be just using the edge is one path, or using the other wiggly blue thing would be another path. So these are two different paths. If I take, this one is a path, this yellow thing, and this green thing is a path between U and V, and the green thing is just one edge long, right? So that would mean that there's at least two paths from U to V, which is a contradiction. Okay, so having a unique path between two vertices implies that you're connected, and T minus E is disconnected. So in particular, being a tree implies these things as well. So now, to kind of complete this equivalence, okay, so remember I wrote three different things here. So what we've proven so far is that being a tree implies 1 and that 1 implies 2. I'm not going to bother with 3 right now, okay? So 3 is kind of related to your assignment, so I'm not going to prove it because then I would be just giving away the assignment question. But what I'm going to prove now is that 2 implies that T is a tree, okay? Which will then imply that all of these things are all equivalent because, for example, 1 implies that it's a tree because 1 implies 2, which implies that T is a tree, right? So we'll have this kind of cycle of equivalencies. And yeah, this one I'm not going to prove because it's on the assignment. Okay, so we're going to prove that the second condition implies that T is a tree. So suppose that T is connected and that T minus E is disconnected for all edges, and I want to prove that T is a tree. So this is my assumption, this is my conclusion. Now, it's not too bad because so remember a tree is connected and acyclic. The assumption has given us half of that already, right? We're already assuming that it's connected. So all we need to show is that it's acyclic. Now, imagine there is a cycle, right? So the graph is connected and somewhere in the graph there's a cycle. So here's the picture kind of down in this corner. Now, if I delete an edge from the cycle, what happens? And I claim that the graph stays connected. So maybe I'll do this on a different slide. So I've got a connected graph that has a cycle, okay? So I don't know what the rest of the graph looks like. That doesn't look very connected. I've got whatever on the rest of the graph, I don't know, but somewhere I've found a cycle and there's an edge E and the graph is connected. So suppose we delete the edge E. So here we've got a graph is connected and E is in a cycle. So I've drawn the cycle and so this is the edge E. And now let U and V be any vertices of this graph T. And I want to say that the graph is still connected. So my question is there still a way to walk from U to V after we delete the edge E? And if so, yeah, why? Yeah, I'm not sure whether this should be obvious or not, but well, so the answer in the chat, the answer of yes is correct. And here's how you can think about it. So imagine I just go back to the tree or the graph T. So it's not necessarily a tree. We're trying to prove it's a tree. I look at U and V. And in T, there exists a path or, a walk or a path or whatever that goes from U to V. So if the walk in T didn't use E, then I'm happy, right? Because after I delete the edge E, it didn't make a difference, right? This walk didn't get broken. But now suppose it does use E, and I delete the edge E. And the kind of key thing here is that, okay, now I'm going to kind of draw the same picture up here somehow. So imagine I've got U and V here and here, and I take a walk from U to V that uses the edge E, and then I delete the edge E, and it breaks this walk, right? It kills it. But I'm sort of okay because I've got the cycle, so I can actually just go the other direction. So that's the kind of key point here. I can go, I can follow the same walk until I get to the first vertex of the edge, of E, and then I can, instead of going through E, I can go the other way on the cycle until I get back to the other endpoint of E, and then I can go this way. So I can still get, I can do this, I can still get all the way from U to V. So I start there, I go here until I get stuck, I go the other way around the cycle, and I go to V. Okay, so what we've proven then is, well, what I wrote on the previous slide. So if T is connected and T minus E is disconnected for all edges, then T is a tree. And we proved that, just to make it clear, we proved that by, we could think about it as like by contrapositive or contradiction or whatever. So we assumed that T wasn't a tree, which means it must have a cycle. And using that cycle, we proved that there's an edge that you can delete such that the graph stays connected, which contradicts the hypothesis. So that was a contradiction. So this is like a, so there's still a path. So in other words, T minus E is connected, which is a contradiction. So there's lots of stuff about trees that can be proved in a very similar manner.